just got a set of games dice. They're supersized and they're blank. So if you ever want to play a really boring game, you just get a bunch of these and you roll them, and the state determines what you do. Kind of boring. But what I'm going to do is I'm going to actually mark these with my own custom Amazon Basics Sharpie. And what I'm going to do is I'm going to think of this as the Bloch Cube. I'm going to mark the opposite faces of this cube with distinguishable states. So I'm going to call one the 0 state. I'm going to call the other one the 0. One of them will be the 0 state. One of them will be the 1 state. And then the question is, what do you do with the other faces? Well, we'll see in a second. Okay, so I've labeled 2 of these. This one is the 0, and this one is the 1 state. Pretty classical so far. But all these other states, they are unlabeled right now. But what I'm going to do is I'm going to give some meaning to the other states. So they're also going to be kind of like the 0 and the 1 in the sense that they will be distinct from one another, but they're going to be linear combinations of the 0 and 1. All right, so now I've got the 0 state, I've got the 1 state, but now I have 2 more states, which I'm going to call 0 plus 1 and 0 minus 1. Now, for those of you who know something about quantum mechanics, you'll know that these are not normalized states. So I'm not going to worry about them unless you really, really want me to. So I'm not going to worry about them because I didn't hear any objections. All right, so now it's finished. So notice I have the 0 state and I have the 1 state, but then I have 2 other possible combinations. I have the 0 plus 1 and the 0 minus 1. And I also have the 0 plus I times 1 and the 0 minus I times 1. Now I'm not going to worry about the orientation of the state. That's not going to be a part of what I'm considering here. However, the idea is that this is going to be a qubit, and if I were to randomly put it on the table, it might be in a state that is in 0 or 1, but it could also be in a state that is in the 0 plus I state or the 0 minus I state. And the probability when you perform a measurement, you have to ask a certain question. And the question that you ask can be, in this approximation, can be of one of 3 types of questions. One of them can be, are you in the 0 state or the 1 state? It can be, are you in the 0 minus I state or the 0 plus I state? That's the second question you can ask. And the third one is, are you in the 0 plus 1 state or are you in the 0 minus 1 state? So depending on what state you're in and what question you ask, you might get a definite answer or not. So for example, if you happen to be in the 0 state and you ask the question, are you in the 0 state or in the 1 state, the answer will be that you're in the 0 state 100% of the time. And similarly, if you are in the 1 state and you ask, what state are you in? Are you in the 0 state or in the 1 state? The answer will be, you're in the 1 state 100% of the time. Now, if you are in the 0 plus 1 state and you ask the question, are you in the 0 state or in the 1 state? It turns out that quantum mechanics will say that you will find that you are in the state 0 50% of the time and in the state 1 50% of the time. And in fact, that's true. That's also true for this state and for this state and for this state. So for all of these states, if you ask the question, are you in the 0 state or in the 1 state? quantum mechanically, you will get an answer that will be 50%. 50% of the time you will get the answer that you are in the 1 state, and 50% of the time you will find that you are in the 0 state. Now here's the weird thing. You can ask different questions. So right now we've only been asking, are you in the 0 state or are you in the 1 state? But there's really nothing special about that state. So for example, you could say, you could be in the state 0 minus 1, and you can ask the question, are you in the 0 minus 1 state or are you in the 0 plus 1 state? And the answer would be that you are in the 0 minus 1 state 100% of the time. And the same thing would be true here. If you are in the 0 plus 1 state and you ask, are you in the 0 plus 1 state or the 0 minus 1 state, you would get this as the answer 100% of the time. But now, all the other questions, when you ask them, if you say, are you in the, if you're in the 0 minus I state, I times 1 state, and you ask the question, are you in the 0 plus 1 or the 0 minus 1, you will get 50% of the time you will find that you're in the 0 minus 1 state, and 50% of the time you will find that you're in the 0 plus 1 state. So the point is that if you are asking the question about which you are in one of the faces, so for example, again, if you're in the 0 minus I times 1 state, and you ask, are you in this state or are you in this state? You will always be in this state. You'll find that you're always in the state 100% of the time. But for the other 4, it will be a 50-50 toss-up. If you're in any, if are in any of these other 4 states, and you ask the question, are you in this state or in this state? The answer will be that you'll be one in the other 50% of the time. So if you think of the 6-sided dice, when you ask a question, you're asking the question about an axis, either this axis or this axis or this axis. And so the possible answers are the 2 opposite faces of the die. And so when you ask a question in quantum mechanics, you're asking a question that is only along a certain direction. And the answer will be definite or indefinite depending on whether you are in one of these states or in one of the other states. Now, the reality of quantum mechanics is that there is a whole, this is really not a square or cube, it's a sphere, and the relative probabilities are not always 50-50, but the idea are essentially captured by this cube.